Okay, so I would say that we could start. I see we are mostly, I mean, the number of participants is still growing slowly, but allow me to welcome you all to this webinar, which will be focused on biohydrogen for the sustainable energy transition, developments, opportunities, and challenges. As you know, this webinar is organized by the Global Bioenergy Partnership, which is an international initiative mainly focused on bioenergy. Sustainability of bioenergy is one of our main priorities. My name is Maria Michela Morese. I'm the Executive Secretary of the Global Bioenergy Partnership, and we are organizing this specific webinar in the context of an activity group of the Global Bioenergy Partnership, which is the activity group which deals with wood energy specifically. So it's this webinar today is a kind of explanatory, exploratory attempt to understand better, raise the understanding and the awareness around biohydrogen, because we know that it's a very attractive fuel option. We have different production processes, and we will have today a couple of presentations that will give an overview regarding the possible applications, technologies of biohydrogen. So allow me to introduce the first speaker of today. Good morning, Suani Coelho, a colleague from Brazil. I can't see the list of attendees while speaking, but I would like to give the welcome to all the colleagues, friends, and colleagues that are connected with us in this webinar. So the first speaker of today, it's Abhijit Borol, from the University of Tennessee, research professor. Abhijit has a 20-year experience in bioprocessing, biomass conversion, waste to energy, and bioelectrochemical systems. His main goal is to develop the waste to hydrogen pathway using bioelectrochemical systems, which can impact the waste problem, availability of zero-emission fuel, and climate change. He is currently focusing his efforts to cover the thematic area of water energy food nexus, which is extremely important, spanning from biorefinery and bioenergy industry to the oil and gas industry. Abhijit will give an overview of the role of biohydrogen in the biorefinery. So Abhijit, floor is yours. Thank you.
Thank you. I'm going to share my screen. Hopefully you all can see it now.
Yes.
Yes.
Okay, perfect. So I'm Abhijit Borole. As Mariana said, I'm a research professor at the University of Tennessee, and most of my life I have been an academic, primarily at UT as well as at Oak Ridge National Lab, where I spent over 20 years. And in the last few years, I've also been active in the startup that we founded a few years ago. So today I'm going to present to you a lot of work that was done at Oak Ridge National Lab at the University of Tennessee, and touch upon briefly how we're trying to take this technology commercial. So as we all know, there's a significant energy transition going on today, and there is a big move towards electrification. However, there is also a lot of push for hydrogen, and the hydrogen economy is really growing up. And there is a need for also changing the fuels that we use for aviation and marine transport. So whether the answer is biofuel is a question. In addition to transportation fuels, there is also a need for changing and moving from petroleum-based energy to other clean energy for cement, steel, and other kind of industries. So hydrogen has significant drivers and challenges that are coming up, and over the last 3 years, there has been a ramp up in all of these by different countries and different corporates moving along to really contribute to hydrogen production. Today's challenges remain developing the infrastructure for producing hydrogen, and also the developing carbon negative or green hydrogen solutions. So again, biohydrogen is a good candidate, and we'll discuss that today. So in terms of biohydrogen production pathways, there is the fermentation pathway, which is basically conversion, anaerobic conversion of sugars and other molecules into hydrogen. The second pathway is biophotolysis, which uses light and microalgae or other photosynthetic bacteria to produce hydrogen. And the third one is microbial electrolysis cells, which is an integrated biological and electrochemical catalysis pathway to convert organic molecules into hydrogen with application of a small voltage. So this slide sort of gives you a starting overview of the potential for producing hydrogen from these particular technologies. So starting with fermentation, in comparison to the hypothetical hydrogen production from a molecule of glucose, which is 12 moles, in fermentation you can only produce 4 moles of hydrogen per mole of glucose. Practically, you have about half of that observed in the lab as well as at full scale. The second one is a modification of that, where we combine photofermentation with dark fermentation, and that way you can actually increase the yield of hydrogen to 12 theoretically. Practically, there has been numbers like around 7 moles of hydrogen per mole of glucose that have been reported. The third one, which is the microbial electrolysis, also capable of producing 12 moles of hydrogen, and the yields observed have been slightly higher in this particular technology, and this is a very new technology. So, in comparison to the non-biological routes for converting, say, sugars into hydrogen, there's one autothermal reforming, which can produce 10 moles theoretically and practically about 9.5. And also the biomethane pathway through SMR, which is 8 theoretical moles and 6 observed moles. So in order to move the fermentation process, developing commercial technologies based on fermentation, there are a few limitations. Besides the 4 moles of hydrogen per mole of glucose, there are also significant amounts of volatile fatty acids which are produced in the process and which result in high effluent BOD, which cannot be disposed of very easily. Also, there may be pretreatment requirements for removing inhibitors, and there's a need for separation of hydrogen from carbon dioxide, which is produced in the process. There is definitely a lot of scope for improvement fermentation processes, particularly in combination with photofermentation, as I indicated earlier, and developing these photobioreactors for combined dark light fermentation or separate fermentation is one of the pathways for improving these technologies. There's significant work also going on in genetic engineering of microbes to improve the hydrogen yield through metabolic engineering as well. If you look at biophotolysis, which is a way to use light in combination with the biological process, always the problems with the photo reactors is the penetration of light to really provide the energy required for conversion and production of hydrogen. One issue with these streams is typically because you want to use waste streams for producing these hydrogen or biomass, and a color of the stream can be an issue in those cases requiring pretreatment, which essentially ends up in removing the substrate instead of converting it. Also, if you use open bioreactors, there's a fear of contamination. There's a pH range in the acidophilic range, and also requirement for critical carbon to nitrogen ratios for these things to work, because they use nitrogenase enzyme as a way to produce hydrogen. And besides that, the typical intensity, light intensity and spectrum requirement depending on different bacteria. There is definitely potential for improving this further. However, the rates of production via photo systems is really low, but that also means there's significant improvement possible through, say, genetic engineering or improved cultivation methods, or engineering the photosystem 1 and 2 enzymes, using different light spectra and also bioreactor design. So I would like to move into the microbial electrolysis technology, which is where I have done most of my work and focus on this. One of the things with this technology, as I indicated earlier, is that you can produce 12 moles of hydrogen per mole of glucose through this technology, and there's potential to really use electricity which is available in abundance, and sometimes we have to not use it because of batteries not being available and so on. So microbial electrolysis is a way to really combine biology and electrochemistry to make the hydrogen. And similar to the other processes, this also has a number of limitations which can be addressed by improving the process design, system design, as well as biological parameters. So the key to this process is the biofilm, which is actually capable of converting sugars and other molecules into electrons, which are then converted into hydrogen through the electrolysis, kind of partial electrolysis process. The key to this is the electroactive bacteria, which actually do electron transfer, which is direct electron transfer from the microbe to the electrodes. So this allows the process to really have a high efficiency. And I show here a couple of pie charts, which are basically different microbial consortia developed for treating waste and biomass related streams into hydrogen. The typical microbe that has been utilized in these systems is Geobacter sulfur-reducens and other Geobacter. And in typical consortia for production of hydrogen in these systems, it can be as low as 7 to 10%, but also as high as 90%. So now I'd like to look at the interface between biorefineries and hydrogen. So there are three main pathways which are looked at in biorefining for producing biofuel and other kind of building blocks that we need for the future. So the biochemical pathway, which uses fermentation of biomass to make alcohols and other products. This is one pathway we will look at. The other one is thermochemical, which uses pyrolysis or gasification of biomass to make products. And then the third one is algal feedstocks, which are typically processed via hydrothermal liquefaction to produce a bio oil, which can then be converted into biofuels. So starting with that as a background, we have done work with several different kind of biomass as listed here, and work with different national labs and USDA labs as well. And typically a lot of these, the biomass conversion into biofuels is one of the main targets that is being developed at these national labs. So what in these collaborations, we work with these national labs to basically use the waste streams that they provided to make the hydrogen, and also looking at different kind of pretreatments, including pyrolysis, hydrolysis, and so on. So I would like to give you an overview of the potential performance metrics that we can obtain for these kind of systems, and then go into the details of how this can be implemented in the biorefinery. So to start with, I would like to talk about the performance criteria for microbial electrolysis. Of course, the hydrogen productivity is a main target for achieving commercial feasibility. And then there's a lot of other efficiencies related to conversion of waste into electrons and then into hydrogen. So they correspond to the anode efficiency, cathode efficiency, COD removal efficiency, as well as electrical efficiency. So if you look at the numbers here, we have listed commercial potential targets for these kind of systems to be achieved in order to generate hydrogen at a reasonable price, and then list some results that have been obtained at the lab scale for biochemical, thermochemical, and algal refineries. So interestingly, in the last few years, the target for hydrogen production, which is a rate over 15 liters of hydrogen per liter of a reactor per day, has been achieved through using some of these streams, as well as the efficiencies of producing the hydrogen from waste materials and biomass has been demonstrated, which makes it encourages you to look at developing this technology at commercial scale. So some details about the biochemical conversion pathway and how microbial electrolysis can be coupled to the typical biochemical refining process. This work that was conducted in collaboration with the National Renewable Energy Lab using corn store as a feedstock, the hydrolysis process to break it down into a liquid stream, which is fed to a fermentation reactor. And the effluent that comes out of fermentation, which is basically unconverted molecules, was then used to make hydrogen. So this essentially allows you to improve the overall energy efficiency of the process, as well as produce hydrogen for other uses. The second one I'm going to talk about is pyrolysis, microbial electrolysis, which is a way to convert biomass into biofuels and hydrogen through this pathway, which integrates pyrolysis and microbial electrolysis. So what was done in this example was switchgrass was pyrolyzed, producing a bio-oil, and then the bio-oil was separated into an aqueous phase and an organic phase, because as many of you may know, there's a significant high oxygen content in bio-oil, as well as high water content. So in order to make biofuels from oils that are derived through biomass pyrolysis, you have to do a lot of hydrogen of oxygen removal or deoxygenation, which requires hydrogen. So the concept here was to provide that hydrogen through the aqueous waste produced from pyrolysis through microbial electrolysis, and then generate hydrogen. So this results in two different potential products: the hydrogen as well as the bio-oil, which can then be converted into liquid fuels through deoxygenation via the renewable hydrogen that is produced. The other refineries that have been looked at are using algae as a feedstock. And in this example, the algae were basically broken down through hydrothermal liquefaction, producing a bio-oil. And then aqueous part of that bio-oil was actually used to produce hydrogen. And in this process, because of the high nitrogen content of algae, you're actually able to also potentially produce a side stream of ammonia, which can go into fertilizer production and so on. So in this way, you can actually, in this particular process, we had also looked at nutrient recycle to allow the minerals and so on to be recycled into the algae pond. So this really results in a circular algal biorefinery kind of concept. So when you want to apply these different concepts at the biorefinery scale, here is one example, because you want to be able to integrate the processes with mature technologies. And so this gives one example of how that can be done in a biochemical refinery, where you could use a AFX treatment, or using ammonia, or consolidated bioprocessing, which produces ethanol, but then the solids can be used to gasify and produce syngas, which can be cleaned up to use a Fischer-Tropsch synthesis feedstock. But you do require hydrogen for that. So in this particular mature pathway, you could do that through a wastewater treatment, producing methane and partial oxidation of the biogas. However, if you are able to use microbial electrolysis, as we showed, you can potentially directly produce that hydrogen and supply that to the Fischer-Tropsch synthesis to increase the hydrogen content of the feed. Going to the pyrolysis kind of process, you could, as I indicated, you could use the hydrogen that can be produced through microbial electrolysis and deoxygenate the bio-oil to produce biofuels. And similarly for algal fuels, where you could take the algae, make the bio-oil, and then use the hydrogen to basically produce a clean biofuel, at the same time potentially have hydrogen for individual sales as well. So when you want to integrate all of these processes into a biorefinery, there's a significant need for really going from fossil fuel based economies to biomass and bioeconomy. And so you have a whole palette of products that we generate today from petroleum. So in order to make that, convert those into the materials and the feedstocks we need for our 21st century, you want to be able to use the current economy, which is moving towards electrification. So how can you combine the biomass and electrification? So the pathway to that could be through a bioelectrorefinery, where you could produce hydrogen and then also produce a number of other products that we require for the economies today, including fuels, food, as well as chemical feedstocks, which would then go into producing bioproducts, polymers, fertilizers, and so on. So when we look at the pathway to commercialization, I talked about biomass and algae. One of the things we have been looking at, as I indicated, I'm also part of a startup. We found out early on that there is another feedstock which might actually be very much feasible to use for producing hydrogen, and that was food waste. So similar to biomass that's available in around 1.3 billion tons in the US, the food waste availability is around 1.3 billion tons around the world. So that's a significant waste of resources. So that's one of the feedstocks we have been looking at in order to make hydrogen. And we have a pilot study going on in South Korea based on microbial electrolysis using food waste as a feedstock to produce green hydrogen. And in the simplest way, you could produce a second byproduct from this, which could be taking the unconverted material from the food waste and return it back to the agriculture as a fertilizer. So you could return NPK as well as the carbon back to the soil in order to really create a circular process. So one of the things we are looking at is to be able to develop these circular and inclusive process, converting, say, food waste into a fuel like green hydrogen, and then fertilizer and a water stream, which can also really contribute to, all of these can contribute to not only CO2 emissions reduction, but also to the other ESG parameters that are really critical for many of the corporates today as we move towards a clean economy and a circular economy. So with that, I would like to wrap up and summarize our discussion. We talked about the pathways to biohydrogen and how dark and light fermentation and MEC technologies can lead the way. The feasibility for using real waste streams and biomass, and the key parameters being efficiency and productivity of hydrogen for making this possible, and how we can integrate the MEC technology into biorefinery and make hydrogen for producing clean biofuels as well, and targeting sustainable aviation fuels and marine fuels. And the ability to actually take food waste as a negative cost feedstock to make hydrogen, and look at a simplistic path to really enter into the circular economy using food waste to produce fuel and food, additionally in a circular process. So with that, I would like to acknowledge a lot of the work that was done here at Oak Ridge National Lab, as well as the US DOE for the funding, and then collaborators at the different national labs. With that, I will stop and transfer the screen back to you.
Thank you. Thank you so much, Abhijit. It has been extremely interesting, informative. You've guided us through all the various processes. It was interesting to notice the variety of biomass that you mentioned that could be used. And it was extremely interesting also to see at the circularity approach you stressed more than once. So the importance to look not only at the energy production, but also at the bioproducts, which is the win-win of these kind of technologies, looking also at soil fertility rather than nutrient rich water. So thank you so much for this extremely interesting overview. I already see a number of, I already see a number of questions being raised in the Q&A and in the chat, but we'll leave those questions for the discussion session. For the time being, we go ahead with the next presentation. Filomena Pinto Filomena is senior researcher at the National Laboratory of Energy and Geology in Portugal. Filomena will give an overview of biomass gasification for biohydrogen research frontiers. Allow me to present Filomena. Filomena Pinto's main research areas cover thermochemical conversion technologies, coal, biomass, and different types of wastes. Her current efforts cover mainly pyrolysis and gasification processes to produce biofuels. She has tested a large range of biomass types and a variety of wastes in fluidized bed gasification. And her current main goal is to develop syngas cleaning and conditioning procedures. Well, I would say that without further ado, I give the floor to Filomena for her presentation. We have another 20-minute presentation from her side. Over to you, Filomena. We see your presentation. Gorgeous. Go ahead. Thank you.
Good afternoon. It's my pleasure to be here today in this webinar. So thank you for the invitation and thank you for your presentation. So my presentation will focus on one of the processes to produce biohydrogen, that is biomass gasification. I will start this presentation by a small introduction to the subject. I will move on to the general layout that leads from biomass gasification to biohydrogen. I will speak a little bit, because time is short, about biomass gasification technologies, cleaning and conditioning processes, and also about some separation technologies for hydrogen. Before finishing my presentation, I will speak a little bit about some main routes for biohydrogen productions, and I will finish with some key message. So gasification is a thermochemical conversion process that is suitable for a wide range of feedstocks. In fact, this is one of the main advantages of gasification. It's the possibility of dealing with different feedstocks, use it alone or mix it to one another, and obtain high fuel conversion. Technologies are suitable for different scales, and the gasification gas may be used in different sectors. Besides heat and power generation, it is possible to produce transport fuels and chemicals. Gasification has fewer technical limitations than other advanced biofuels technologies, and it's possible to integrate it with other technologies. So to start, I will like to focus that it is possible to gasify a lot of feedstocks from biomass, like sweet sludge, forestry biomass, other industrial wastes, energy crops, and so on. But also it is possible to gasify other types of wastes, like plastic mixtures, used tires, RDF, and so on. And it is also possible to prepare different mixtures of all these feedstocks. Nowadays, there is a rising interest in gasifying poor quality materials, but this brings some challenges, because if these materials contain undesirable elements, so unwanted compounds will be formed and released to the syngas, which is going to make more complex the cleaning and conditioning processes of syngas. So syngas may have different applications. The more developed ones are the heat and power generation by using syngas in gas turbines, engines, fuel cells, or boilers. But as mentioned before, it is also possible to produce fuels by chemical synthesis. Some of them, the most important, are presented here. Syngas may be also used to obtain hydrogen. And as mentioned in the previous presentation, it is also possible to use syngas in anaerobic fermentation to produce bio-basic chemicals. So nowadays there are much information about gasification and there are much knowledge. The gasification main research areas focus on syngas utilization to produce biofuels and biochemicals, to produce synthetic natural gas, to achieve capture, storage, and utilization of CO2 from gasification process. Another area is to study the possibility of doing soils impregnation with biochar produced by gasification, and of course, the theme of today's presentation, the production of biohydrogen. So there is a long way from the gasification process to the production of biohydrogen. So after production of syngas, cleaning and conditioning processes are very important, because gasification gas composition depends not only on the gasification technology and conditions, but also on the feedstock that is used for the gasification. And when the composition of the initial syngas is quite different from the composition that is required for the syngas utilization, cleaning and conditioning may become very complex, which increases the capex and opex. So moving a little bit to the biomass gasification technologies, there are different possibilities: a fixed bed, fluidized bed, and infinite flow gasifier. They require different gasification conditions, namely at temperature. Infinite flow gasifier is the technology that requires the highest temperatures and the lowest particle sizes, and the choice of one of these technologies depends on the feedstock that we want to gasify and on the application that we want to give to the gas that is going to be produced. If we want to obtain hydrogen, it's important that the syngas is free of nitrogen. And we have two options: autothermal gasification, where the heat that is needed for the gasification process is produced inside the gasifier by the partial oxidation of the feedstock. But if we want to produce hydrogen, air should be used, but oxygen is the best option. If we choose allothermal gasification, then it needs to be supplied. So now I will like to move to some more recent gasification technologies. And I will start with the dual fluidized bed gasification. In this case, we have two sections, the gasification one and combustion one. In this case, the feedstock is burnt in presence of air to produce heat that is going to increase the temperature of the bed material that moves to the gasifier and supplies the heat that is needed. So char and bed material is again transported to the combustion reactor to start the process. There are some main installations that have tested with success this technology. Newly gasification technology is similar to the previous one, but here we have the gasifier section that it's here. It's a riser where biomass and steam is introduced together with the hot bed. At the top of this riser, there is the separation of the gas and the solids go again to the combustion zone to be heated. In the heat pipe reformer, the concept is different because we don't have a bed material. We have the heat is supplied by a heat pipe. So we have heat pipes that are filled with a carrier, that in the combustion zone evaporates, and in the gasification zone condensates and releases the heat that is needed. Another concept is the sorption enhanced reforming, where two reactors are used, combustion reactor and gasification reactor, and a circulating loop. Here, in combustion reactor, limestone is used, and the calcium carbonate releases CO2 and forms a calcium oxide that goes to the gasification reactor and reacts with the CO2 that is released by the gasification reactions and forms again calcium carbonate that goes to the combustion zone. So by this process, it is possible to obtain a syngas rich in hydrogen and poor in CO2. If we compare syngas compositions obtained by these technologies, we find that the SER produces the highest hydrogen and the lowest CO and CO2, and the TAR is also low. So next, we have to concentrate in the cleaning and conditioning processes to remove or at least decrease the contents of the main impurities, particulate matter, tar, ammonium, hydrogen chloride, and hydrogen sulfide. So the cleaning and conditioning processes depends very much on the initial syngas composition and also on the syngas application. There are two main options: cold gas conditioning, where low temperatures are used, and here we may choose dry scrubbing or wet scrubbing, or we may choose hot gas conditioning, where the gas is treated at high temperature by thermal catalytic cracking processes, besides others. So this process is a good option if the syngas needs to be used in process that requires high temperature. So here are a list of some syngas conditioning processes to remove different impurities. But I would like to call your attention to tar, because tar is a big problem in the gasification processes. And for tar abatement, different types of catalysts have been developed and tested, some of them with good results. Moving next, now I would like to speak a little bit about the water-gas shift reaction, because it allows to increase hydrogen content in the syngas by the reaction of CO with steam. Different processes and different catalysts may be used, some resistant to sulfur poisoning, some others don't. And in this last case, it is necessary to concentrate in the cleaning processes to decrease sulfur content. For an example, I could mention the tests done in the Overwatch plant in Austria that have tested with success 3 fixed bed reactors in series using commercial catalysts. There are many cleaning and conditioning processes. I don't have time to mention all of them, of course. So I would like to refer to important ones for the biohydrogen route. It's the tar removal by rapeseed oil methyl ester scrubber that by syngas decreasing temperature, steam is condensed and tar is removed. This process may have a problem of the production of a waste stream, but this problem may be more or less solved by the burn of this stream to produce energy. Another cleaning and conditioning process that I would like to mention is the CO2 removal by amine scrubber. Different amines have been tested, but the activated MDEA with piperazine have shown good results. However, there are still some issues that need to be solved, like the significant amount of energy that is needed for the regeneration step, especially when hydrogen sulfide is present. There are also some problems related with the loss of liquids that needs often refilling, and also the formation of non-soluble salts and foaming that brings some problems, and also some corrosive due to the behavior of amines. So moving to the separation technologies, there are also a large number of options. I would like to mention only two, because they seem to be the best ones for the production of biohydrogen. One is the PSA, pressure swing adsorption, where the flue gas is compressed when entering the PSA vessels. The vessels that are not in contact with the feed, the syngas, are regenerated by lowering the pressure. And this concept was tested in Oberwart plant, where 4 vessels filled with activated carbon were tested with good results, because high hydrogen purity and high hydrogen recovery were reported. Another option is the gas permeation membranes, where the feed gas goes into a vessel that contains a membrane, and only hydrogen is capable of going through the membrane. So we obtain a stream called permeate that contains only hydrogen, and the other gaseous spaces remain in the retentate. So the challenge is to achieve high hydrogen purities, and also to achieve high hydrogen recoveries. That is to say, the retentate should contain low hydrogen content. So different types of membranes have been tested, polymeric, porous, dense metals, and so on. And some of them are available at a commercial scale. So I would like to show to you 2 possible routes for the hydrogen production that have been tested and studied with some success. One of them is based on the dual fluidized bed. So after the gasification, the syngas goes into the water gas shift reaction. Sometimes some cleaning is needed in between these two. Here, hydrogen is produced, so the content of hydrogen in the syngas increases. Tar may be removed by the RME scrubber. The mean scrubber succeeds in removing CO2, and finally, hydrogen is compressed to a PSA unit to produce biohydrogen. The adsorbate contains the other gaseous components, mainly hydrocarbons, and so they may go to a steam reformer to be converted in CO and hydrogen. Another route could be this one presented here, that is based in the SER gasification technology. Here, the complex is lower because as the gasification the gasification gas produced has already a high content in hydrogen and a low content in CO2. The water gas shift reaction is not necessary. The amine scrubber is not needed, and so all the process is less complex. However, The steam needed is lower than in the previous option. The energy is also lower, but the production of biohydrogen is less. Before finishing, I only would like to mention that we are still working in this subject. We are participating in a big project, the Move to Low C, that is in fact divided in several sub-projects, and one of them is the production of biohydrogen for urban public transport vehicles. The project aims to produce biohydrogen from renewable sources, different ones, biogas, biomethane, and biomass gasification gas. And the main goal is the installation and demonstration of the process and the production of hydrogen, to be tested in public transport vehicles. And to finish, I would like to mention some key message. So I believe that in the future, biohydrogen will be a renewable secondary energy carrier, and that the biomass gasification is a good option to produce biohydrogen and also to achieve decarbonization. However, some drawbacks and technological challenges still need to be overcome to improve the overall economic feasibility. Though some technologies are already available in the market, like water gas shift, scrubbers, PSA, for instance, some technological challenge of the overall process still need to be overcome. So demonstration of the full process chain is still needed, and I think that governmental support and subsidies are necessary for the implementation of hydrogen production from biomass gasification. So here is only some of the references that were used for the preparation of this presentation, and I would like to thank you all for your attention.
Thank you so much, Filomena, for this overview. It was interesting to hear also these technologies that are available on the market. It's important, as you said, to go into the demonstration, so it's still needed, and also to get the message that you said. You highlighted the need to get some support in terms of policies, in terms of subsidies. So that's the key points that I take from your presentation, that I would like to remind all our participants that the recording of this webinar and all the presentations will be available on the GBEP website just after this event. Now we have some time to be dedicated to a discussion session. We have a very brief keynote speech from David and Francesco to give an overview of their experience on biohydrogen, and then we go directly straight into the questions that I already see into the Q&A and into the chat. So I will share the screen and project their slides from here. Let me know if you see the screen.
Yes.
Yes, indeed. Yeah. Okay.
Go ahead. You have 4 or 5 minutes. Please go ahead. Thank you.
Okay. Can you move to the next slide, please? So I'm David Lessin. I work for Equitech, and I'm heading the Paris office. It's a go-to-market entity to address France. So what is Equitech? At Equitech, we are an Irish listed company on the London Stock Exchange, and we most exclusively dedicate our time on syngas production technology and innovation for both biofuel and baseload energy. We have developed a proven proprietary patent gasification technology, which converts a wide range of feedstock from forestry to agricultural waste, industrial waste, and also RDF and municipal waste as well. And we are able to produce from those waste a synthetic natural gas or syngas for a wide range of applications, from heat, base load power, hydrogen, synthetic natural gas, and other biofuel. We believe that we have a clean emission profile that makes our technology fit for net zero future. And we have the ability to tune our syngas to specific business requirements and application. We have developed an end-to-end approach to design, integration, deployment, and maintenance for technology and engineering, and which typically mitigates the common risks associated with third-party technology, and is able to safeguard long-term value creation for both clients and projects. We have also established a growing ecosystem of local partners in development, delivery, and maintenance to basically ensure that local engagement is in line with local requirements and the evolution of local capacity to support local communities in the EU, UK, and the US. Please, could you move to the next slide? So the market we are aiming to address is 98 trillion, which is the net zero addressable market from now to 2050. Hydrogen is expected to contribute to over 20% of the global carbon abatement by 2050. Our class of technology, which is a thermochemical process, we believe it has reached TRL around TRL 8 and 9. And we believe it's a key pathway to produce biohydrogen, and something that the EU is most focused on progressing capacity for. Hydrogen is a key industrial decarbonization tool, and for instance, with on-premise solutions to address immediate demand and also distributed demand. We believe that actually the EU should incentivize, EU incentive needs to really focus on the best life cycle and end-to-end carbon efficiency and reporting. To you, Francesco.
Okay, I go. I'm Francesco. Okay. Quindi the product of from syngas is different. Synthetics, natural gas through methanation, hydrogen, liquid fuel through Fischer-Tropsch, methanol, electric power, steam and thermal power, and biochar. Biochar, we don't speak about biochar because it's a biofertilizer and is very important for agricultural activities, because there is the CO2 for the soil, where new and more biomass will be produced. This is the last part of the life cycle of biohydrogen. Next slide. Okay, Ecotech. Ecotech is IP, is not a piece of equipment, but a bespoke design capability. Ecotech is a proprietary of the modeling that allow accurate prediction of process quality and quantity of syngas and bottom ash to more or less 5%. Ecotech does as bespoke this design of all components, enable maximum uptake of CO, CH4 and or H2. Ecotech has an exclusive control system to management heat, pressure, charm, and other reaction factor to target relevant feedstock and application combination. Of course, Ecotech technology works because of its end-to-end process focus and know-how. Ecotech has a big feedstock library. More than 16 tested and documented feedstock for a design for efficient operation. Ecotech has the syngas condition painted for the level of purity to suit the application, including ultra pure for advanced biofuel or hydrogen. More important is the continuous monitoring and feedback in real time to allow variation in a control system to improve efficiency and quality of the process for specific feedstock application combination. Next slide. Okay.
1 minute, because otherwise we won't have enough time for the discussion session. So 1 minute, Francesco. Thank you so much.
Okay. Next slide. Okay. The biohydrogen from syngas is a climate positive hydrogen. Is more important in this period. In the EU, we are next few days. EU announced that it want to increase renewable hydrogen production for the next year. Hydrogen is necessary and important. So in this period, there are no different color of hydrogen. The most important for Europe is that for 1 kilo of CO2, no more than 3 kilo of CO2 are emitted. Next generation to go at the end. Okay, in the plant of Ecotech is expect hydrogen yield for 1 ton hour of biomass. Wood chips, for example, produce 50-55 kilogram of hydrogen per hour. Gasification is a key pathway to transform forestry and farming waste into biohydrogen as a thermochemical process. The syngas technology provides low-cost hydrogen production in the waste to energy fuel process. With our partner, we have the possibility to realize the whole supply chain from biomass and waste to storage and distribution for all further purposes. If I want, I stop it now or continues.
Francesco, I would say we only have another 10 minutes before 10 or 15 at maximum, before we close the webinar. So I'd say, because I see a lot of questions in the Q&A, I would, if you don't mind, I would just to go straight ahead with the discussion section, and so that we could give the opportunity the panelists to respond to the question. Thank you so much. Anyway, also this presentation will be available on the website. Thank you so much. So over to you, David and Francesco. I will stop sharing the screen and you have the questions in the Q&A and in the chat. Over to you. Do you see them, David, or do you need any help from my side?
Yeah, no, I see the first question from Olivier, and the answer is not that simple, because basically it depends on what sort of feedstock you're going to, I mean, from a gasification point of view, I would say, you want to gasify. And the entire profitability of every project, so which means also the cost of production, will depend on what you intend to gasify. basically. So there is no ultimate question. And there is also the way you're able to convert carbon, if you know, because some projects may get extra line of, of revenue from biochar, for instance, and not only for producing hydrogen. So it's a sort of complex answer to that.
Maybe we could open the question also to Filomena and Abhijit to.
Oh, of course, yes, yeah.
Yes, I quite agree with the answer of Javid, because in fact, first of all, we have to decide what is the route, what are the technologies that we are going to choose to achieve our main purpose, that it's the production of a syngas with a certain or required composition by the end use. So it is in fact quite complex unless we decide first exactly what are the diagram, what are the units that we are going to choose.
The only thing I would add to that is the cost of or price of green hydrogen today seems to be in the range of $5 to $6 per kilogram. And ultimately, it will need to get down to probably below $2 per kilogram. And so most of these technologies, including the microbial electrolysis, the goal is to really get down. In order to figure out the price for hydrogen or cost of production, there are a little bit complicated issues like were mentioned by other speakers in terms of the byproducts that you can produce and other things. So, but ultimately, I think you do have to be able to sell the hydrogen at a reasonable price. And so that target is probably, going to be going down from maybe $5 to $6 that is a target today to maybe even below $2 per kilogram by 2030.
Yes, I quite agree, because there is some studies with calculations of the hydrogen selling prices, for instance, and for the two main routes that I have mentioned, the double fluidized bed and the other one, the SER. This study presents price values of about 5.5 euros for the SER process, and for the DFD about 2.7. So, of course, in my opinion, the success of all these depends on achieving a good integration of all the processes, in trying to valorize all the streams, to do a good management of the energy balance, and also to find markets for the so-called products, as mentioned before, for instance, the biochar. So a lot of work is still needed to improve the economic viability of this process.
What I would like to stress as well, so I was talking about the difference in terms of cost of biomass, and obviously I've seen the question from Marco. From our own experience, and very recently we have tested on our facility in Lorraine a feedstock which is not bio, which is contaminated plastic. And in this case, the gate fee will reduce dramatically the cost of production for hydrogen, potentially. Below €1 per kilo. So it's an example. There's another, what we've seen also, again, from a market point of view, what happened is that most of the people that are supplying the, companies, sorry, that are supplying the downstream technology with these PCSA, water gas shifts, etc., they are from the petrochemical industry. And what we see is that because they're from the petrochemical industry, their way they cost projects is for very large projects. And they're not used to smaller projects, smaller scale projects. That's number one. And they also, the equipment they design, typically, even for hydrogen, is coming from blue hydrogen or gray hydrogen. And it's for very large scale. So they need to downsize their equipment and to adjust. And I think we're just not there yet, but we, for example, at Equitech, we have 2 projects under a feasibility study in the UK. So we will soon be able to know exactly what will be the cost for it.
Okay. I want to speak about it. It's necessary to train the political leader to each state to understand the possibility to produce hydrogen in a different way from the most common electrolyzer and steamer form. As is well now, hydrogen could lead to the major problem of its transport to the end user. With the plant of Ecotech, is possible build a small plant with a low cost production near close the end of user with a large economy. It's very important. Instead of solar wind plant for electrolyzer. And this is why it's important that the FAO push this energy policy globally with a webinar like this, but with direct action towards the state with the highest CO emission. It's very important, this webinar for the future, if you want a new climate change mitigation.
Thank you very much. David, I would call upon you as moderator to look through the questions, because we see a lot of questions connected to energy, the ratio between energy used and energy produced of biohydrogen, and how to compare the energy efficiency and conversion losses, comparing biohydrogen on one side and the other forms of energy traditionally, let's say, produced, biogas, biomethane, direct combustion. So I would, if you don't mind, I would focus on those 2 questions for you and for Filomena, Abji, and Francesco to reply.
Okay. Well, I think I will give the answer to my my PhD colleagues here, because it's a more technical matter.
I will go ahead and respond to the question regarding the bioelectrorefinery. So for hydrogen production through microbial electrolysis, you do have to provide electrical energy input. And that's typically what happens is if you look at the electrical efficiency, it's about 150% at the lab scale, which means that the amount of hydrogen energy you get is about 50% more than the electricity you put in, because you're actually deriving energy from the waste as well. So that's probably one answer to the question. In terms of the overall energy balance, you can think about, about 50% of the energy that in the hydrogen comes from the biomass or waste, and then the 50% is coming from the other electrical energy input. So that's in general, I could say that, but as scale increases, those numbers might change.
Well, I can add something. For instance, if we use the gasification of biomass and other wastes to produce syngas, and if we use this syngas to produce energy directly, of course, the process is feasible, is economical viable, and it's more easy because we don't need to do too much transformations to the syngas. But for instance, if we boil or if we use this syngas in motors, what happens is that we produce CO2 by the combustion process. If we want, of course, it's good, it's better than nothing, because we are using wastes, and it's a way of achieving some decarbonization. But if we want to improve in the direction of a better environment, the best option is not to to burn the gas for the syngas for the direct production of energy, but it's the possibility of transforming it, for instance, in biohydrogen, because in this way, now CO2 emissions will be produced in the transformation of biohydrogen into energy.
Allora, I know all the plant, biogas, biomethane, and syngas are totally different. For example, for produce 1 megawatt of syngas is necessary only 1 ton of wood chips, for example. For produce 1 megawatt from biogas, about 8 ton at least. There are more cost, more liquid. Digester is complicated during the whole period of the year. So are totally different, but it's important all this plant, biogas, biodigestion, and syngas, but are totally different.
I quite agree with you, because in my opinion, it's very important to diversify the processes for energy production is fundamental, and not concentrating only 2 or 3.
And we are seeing exactly this issue of energy diversification, energy security in this specific period right now.
That's
Indeed, unfortunately. We still have another couple of minutes before we have to close. And I would say I see that some of the questions that are in the Q&A are being or are in the process to be answered right now. But there is one which seems not to be addressed. We know that hydrogen compression and transportation can be difficult. Do you think there is room for innovation and technology development in this field? If so, can you name some companies and or research institutions that are working on solutions for the transportation of this fuel? Over to you, speakers and colleagues. So in particular, solution for transportation.
The transport of hydrogen is very complicated. Normally, at least 100 kilometers from the plant is a good distance. More distance is not economical for hydrogen. In fact, when I speak about first, is more easy have the plant near the end user that instead with the biomethane or other fuels, there is no problem. Pipeline, on the pipeline go the biomethane where you want. I think hydrogen is very complicated. Compressed, liquid, very complicated.
And I don't know if Abhijit or Mena, if you wish to reply to this question, otherwise I have something very specific on gasification.
Well, if we don't have much time, you can send me the questions and I will reply directly to the persons.
Just in a flash, there is a very general question saying, do we have any experience with gasification and BESS? So bioenergy, BESS, bioenergy capture.
Well, me particularly not specifically, but it's, in my opinion, it's a good way to achieve decarbonization, because in some of the processes that I mentioned, CO2 streams are produced and they may be used to produce hydrocarbons, other fuels. So it is possible to improve the overall process to decrease the release of direct CO2.
Mhm.
So it's another possibility. Of course, TRL of these processes are low. Nowadays are still low. But it's one of the areas of research that seems to be interesting.
Thank you so much. Thank you for this answer. I see there are a couple of questions where David and Abhijit are currently typing to reply. But unfortunately, we are going out of time. So I would like to close this webinar, thanking all the speakers, so Filomena, Abhijit, and also David and Francesco for sharing their experience, their researches, studies, and also the experience of EQTech. So we may take as take-home messages that biohydrogen is a promising and attractive fuel option. Of course, we've looked at pro and cons, so it was extremely interesting to look at the advantages and disadvantages to be faced in all the various production processes. It's important to highlight the circularity. So the bioeconomy approach is very, very important because it brings win-win opportunities, win-win solutions. Looking at bioproducts as well. It was clear that it still requires further piloting and demonstration. Some more support from government in terms of policies would be appreciated, as far as I heard. We've gone also to the issue of costs, also, which is extremely important in certain terms of evaluations, but without forgetting, of course, that we look at the sustainability of a value chain. We look at the 3 pillars of sustainable development: environmental impacts, social impacts, and economic impacts as well. So with this, I would like to close this webinar. I would like to thank you again for your participation, sharing your experiences and expertise. All the presentations and the recording of this webinar will be available on the GBEP website very soon. And as Global Bioenergy Partnership, we will continue exploring more and more with your support and your contribution towards this biohydrogen opportunity. So thank you so much for your participation.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye now.